Today we are going to understand what happens when threads block each other from making any progress at all. That is called deadlock, and by the end of this video you will know exactly what causes them, how to think about them, and what real systems actually do about them. Let's get started. A deadlock is a situation where a set of processes or threads are permanently blocked. Each one is waiting for a resource that another process is holding, and none of them will release what they are holding because they are all waiting. Nobody can move and the system is stuck. Let's look at this example. Process A holds mutex 1 and is waiting for mutex 2. Process B holds mutex 2 and is waiting for mutex 1. A cannot proceed until B releases mutex 2, but B won't release mutex 2 until it gets mutex 1, and it can't get mutex 1 because A is holding it. There is a circular dependency and it won't break unless someone from outside breaks it. So, when exactly does deadlock occur? Edward Coffman identified 4 conditions that must all hold simultaneously for a deadlock to be possible. First, mutual exclusion. At least one resource must be non-shareable, which means only one process can use it at a time. Think of a mutex, a printer, a write lock. Second, hold and wait. A process must be holding at least one resource while waiting to acquire more resources held by other processes. Third, no preemption. Resources cannot be forcibly taken away from a process. A process must voluntarily release them when it is done. And fourth, circular wait. There must be a circular chain of processes. P1 waits for P2, P2 waits for P3, all the way back to Pn waiting for P1. Remove any one of these and deadlock cannot occur. If all 4 are present, then you are at risk of a deadlock. Let's go through each condition in more depth. Mutual exclusion is usually not something you can eliminate. A mutex, by definition, allows only one holder at a time, so you often just accept this condition. Hold and wait looks like this. A thread acquires a database connection lock, then while still holding it, tries to acquire a file lock. No preemption is why we cannot just take a mutex away from a thread. Doing so mid-critical section would corrupt shared state, so held lock must stay held. Circular wait is the condition most commonly targeted for prevention. If you enforce strict ordering, like always acquire lock A before lock B everywhere, a cycle can never form. Before we get into solutions, let's talk about how we visualize deadlocks. The standard tool is the Resource Allocation Graph or RAG. Processes are shown as circles and resources are shown as rectangles. There are 2 types of edges. A request edge goes from a process to a resource, which means the process is waiting for the resource. An assignment edge goes from a resource to a process, which means that the resource is currently held by that process. Look at this example. P1 holds R1. So there is an assignment edge from R1 to P1. P1 is requesting R2, a request edge from P1 to R2. P2 holds R2 and is requesting R1. Follow the edges, you get a cycle. That cycle means deadlock for single instance resources. For multi-instance resources, a cycle is necessary but not sufficient. You would need to do further analysis to confirm if a deadlock has occurred or not, but for a single instance, a cycle is all you need to confirm deadlock. Now, let's talk about what you can actually do about deadlocks. There are four broad categories: prevention, structurally eliminate one of the four conditions before the system even starts running; avoidance, dynamically decide at runtime whether granting a resource request could lead to a dangerous state; detection and recovery, let deadlock happen, detect them, when they do, then break them; and ignorance, which means pretend they do not exist. This sounds like a joke, but it is actually a legitimate design choice in many systems. Let's go through each one. Prevention means you structurally eliminate at least one of the four Coffman conditions. If the condition cannot hold, deadlock is impossible. The most practical approach is eliminating circular wait. You impose a strict global ordering on resource acquisition. If every thread acquires lock A before lock B, then a cycle simply cannot form. No cycle means no deadlock. This is widely used in practice, especially in OS kernels and database engines. The trade-off is code discipline. You have to enforce the ordering consistently. You can also eliminate hold and wait by requiring a process to request all the resources it will ever need upfront before it even starts. If it can't get them all at once, it waits without holding anything. This works, but it's wasteful. Resources that won't be needed for a long time get allocated early, and in practice, processes often don't know upfront exactly what they will all need. Allowing preemption. Forcibly taking resources from a process works for some things like CPU registers or memory pages, but for locks, it is dangerous. Rolling back a thread mid-critical section can corrupt shared state. Avoidance takes a different approach. Instead of eliminating conditions upfront, it makes runtime decisions, checking each resource request before granting it. The key concept is safe state versus unsafe state. A safe state is one where there exists at least one safe sequence and ordering of all processes such that each one can eventually complete given the resources others will release. An unsafe state means no such sequence exists. Deadlock is not guaranteed yet, but the system is in a position where it might occur. Avoidance refuses to enter unsafe state. The classic algorithm for this is Dijkstra's Banker's algorithm. Each process declares its maximum resource needs upfront. When a process requests resources, the OS simulates granting them. It then checks whether a safe sequence still exists after that simulated grant. If yes, grant the request. If no, make the process wait. The limitation is obvious. Processes must declare their maximum needs upfront. In most real-world systems, that's not practical. A web server doesn't know how many connections it will need when it starts. So, the banker's algorithm is important conceptually, but rarely used as is in production. Detection and recovery takes the opposite stance. Do not try to prevent deadlocks, let them happen, detect them, and then break them. Once a deadlock is detected, you need to break it. The options are kill a process, terminate one or more processes in the cycle, simple but lossy, all work done by that process is gone. Preempt resources, roll back a process to saved checkpoint and reclaim its resources. This requires rollback support, which adds complexity. Third strategy is heavily used in databases. SQL engines like InnoDB, PostgreSQL can run deadlock detection constantly, and when they find a cycle, they pick a victim transaction, typically the one that's done the least work, and kill it. The client gets an error and retries. And then there is the Ostrich Algorithm. Stick your head in the sand, ignore deadlocks completely. This sounds irresponsible, but it's actually a rational engineering decision in many contexts. Prevention has real cost, lower resource utilization, complex upfront declarations, and code that needs to enforce strict ordering everywhere. That's engineering overhead. Detection has overhead too. Running a cycle detection on every resource request adds latency to every operation. If deadlocks are rare enough that the expected cost, which is frequency multiplied by the impact, is lower than the cost of prevention or detection, then ignoring them is the right call. You just restart when it happens, which might be once a year. And this is actually what Linux and Windows do at the kernel level for many resource types. Deadlocks in user space, your mutexes, your semaphore, are the programmer's problem. The kernel doesn't help you there. So when you are deciding how to handle deadlocks in your own system, the first question is, how often do they actually occur? The answer determines which strategy makes most sense. That's it for today's video. I hope you now understand all about the deadlocks. If yes, then please do like this video and comment down if you have any questions or if you want me to cover any other topic. Subscribe for more such content. See you in the next one.